Okay, welcome to CTS 120 video lectures. This is John Armke, your instructor, and I'm bringing you in for chapter 2 today. We're going to talk about motherboards and support thereof. So let's look at our objectives for today's chapter. We're going to describe and contrast some various types and features of motherboards that are out there. There's a number of different variations. We're going to look at how to configure a motherboard using BIOS or UEFI firmware, how to maintain a motherboard once it's installed using device drivers, flashing the firmware in BIOS and UEFI, and replacing the CMOS battery in order to retain those settings. Motherboard installation tends to fall into one of three categories, and we talk about this a lot throughout this course dealing with various components. Either a fresh install for a new box, an upgrade, or a failure replacement. So let's look at our types and features. Whenever we're dealing with building a new computer from scratch, one of the first items we must consider is the motherboard. It is the most complex component that's involved because it has to facilitate communication between all other devices inside the machine. We have to consider the following when we're purchasing a motherboard. Its form factor, so how does it hook into the case? Does it have a particular size or shape constraint? What processor, socket, or chipset does it use? That means compatibility for our CPUs. Expansion slots. If we know that we're going to need a particular set of features and the motherboard does not inherently possess it, we have to find a way to include that as part of our expansion. We also want to make sure that in the event of a particular machine for multi-purpose, say, we want to have some expansion slots in reserve to be able to make modifications later. And then, of course, other slots, ports, and connectors for various functions. Remember that a computer can't just magically instantiate a particular change that needs to be there. You have to have the hardware and the software to make it work. And leaving expansion slots open on your motherboard or having onboard connections built in will facilitate that much more easily. So here is an Asus Prime Z370P. This is a very popular gaming motherboard, and you can see that it's got a very clean form factor. Everything's very straight, very accessible. We can see that there are 3 DIMM slots, so it's built for triple channeling, but it only uses 2 at present. We can't tell from looking at it, but if we were to look at the documentation, it would say that it has an Intel Z370 chipset. It's using an LGA 1151 CPU socket. That's an 8th generation based on, again, our documentation here. We can see our PCI Express slots. We'll look at this a little bit more in the chapter, but you can see that 4 of them are the very short ones are X4s. Now, if you were to look at that versus an X1, you would see that there is, again, a little bit of difference, but it's hard to tell perspective-wise when you're looking from a motherboard down. So that's why I always like to check documentation. We also see there are 2 X16s in there at slots, what looks to be 1 and 3. The little blue stems that you see on the end, they almost look like little triangles. Those are lock tabs in order to hold the card in place once it's slotted. Those are indicative of X16s. I personally have not seen them on X8s or X4s. Now, motherboard's form factor will determine several things. The amount of functionality that's likely to be present, because the bigger the board means the more space for connectors. It also tells you what kind of case you're going to need. Once we figured out the case, we can also look at the power supply. Power supplies of a certain size have to fit within a case of a certain size, and that means that the motherboard has to fit as well. This is why form factor is such an important aspect of purchasing components for a new machine. Everything has to be able to work in tandem, so that's why we have this standardization of form factors. Some of the most popular ones we see are ATX, Micro ATX, and Mini ITX. Mini ITX is probably one of the smaller ones that you'll see in conventional circles. It'll sometimes be abbreviated as MITX, MITX. The following slides show us some different comparisons of how they mount and how they're structured. So we can see here a full-size ATX motherboard from Gigabyte. The comparison that I often like to give people is take a look at the stuff that's not likely to change. So if we look on the far left, in the upper left corner, we'll see the VGA connector for the primary video output. We see that there's a DVI connector below it. We also see that there are some USB interfaces. We see that there's a network interface, HDMI. This one's got a lot of features. We see that the audio connectors have all 6 of the conventional ones, so that's left, right, and center with connections for line in as well as the mic. We also see that there are 4 RAM slots. Everything's pretty comfortably spaced out. We see that there are 6 SATA connectors as well as 2 IDE connectors. And we see that there are 5 larger expansion slots, and I think there's one X4 or X1 up at the top, so 6 total. So a lot of functionality on this motherboard. If we move over here to this micro ATX, either the DH676 on the right or the micro ATX from Gigabyte on the left, you see that it's not as rectangular, it's squared off. Something else we notice is that the back panel, the UI shield, IO shield, excuse me, is a lot shorter. We see that there's less information being provided by these onboard ports. So that comparison there shows that we're kind of compressing things down. We also see that the cooler assembly to cover the chipset is a little bit more robust because everything is packed more tightly. And we can see in the Gigabyte board that there are only 4 expansion slots instead of 6. We've also shifted around where the SATA connectors are for the hard drives. Now they are in the on the Gigabyte board anyway, on the bottom right corner. They're now facing parallel with the board instead of perpendicular. So again, some rearrangement. We can see the same thing in the Intel on the right. You can see that there's just kind of some tamping down of where everything fits. And the idea there is that we are removing some space between the capacitors, which means we need more aggressive cooling methods to carry out our operations. Now, furthest of all, we see a mini ITX board here from Asus. So what we see here is that the UI shield, the traditional UI shield that we're used to looking at, IO, I don't know why I keep saying UI, the IO shield that we keep looking at is almost the entirety of the back of the board. If we were to look back at the full size, we would see that it's probably somewhere around, maybe 40% of the back of the board, just under half. Whereas this takes up somewhere in the neighborhood of like 4/5, around 80%. And some of it's arrangement, but some of it's just lack of functionality. Previously, we had an HDMI port, we had a DVI connector. Those are no longer here. We can see that the audio connector now uses only 3 ports instead of 6. We can also see that the RAM is kind of hidden. There's probably only 1 slot that is off behind this big cooler that we have sitting over the top of the CPU and chipset. We also see that there's only 4 hard drive connectors instead of 6, as well as only 1 expansion slot instead of even 4, which was done previously. So we see this one kind of constricts down quite a bit feature-wise. So traditionally, ATX motherboards, being the larger models, tend to be defined by going from anywhere from about 10 inches up to about 12 by 10, 9.6 specifically. And ATX is a very popular form factor. It was developed by Intel in the mid-90s, and it was open source. And open source always tends to propagate well if it's a well-designed product. There's no licensing that has to be paid, so that means, hey, we can use this and we don't have to pay somebody to use it. When you make proprietary formats, then you have to go into a bunch of vendor agreements with different companies and say, hey, in order to use our stuff, you have to pay, X amount per year. So ATX became very popular very quickly. Micro ATX goes from about 7.5 inches square to about 9.6 inches square, 244 millimeters squared. It's a smaller version of ATX by, as we discussed just a minute ago, removing some components, making things a little bit more compressed. Mini ITX squeezes down even further and goes down to up to about 6.7 or 170 millimeters squared. These are used for small form factor boards. They're not traditionally used for high-end performance. They're used for space saving. So you may see them in lower-end computers, really small, slim clients that would sit on a desk that are just meant to act as a web browser or something similar. And in home theaters. Some of the pretty decent high-end stuff that you'll see from, Onkyo or Pioneer or Yamaha, those are going to have Intel boards inside called the Intel Atom. The Intel Atom is what's called a BGA. We'll talk about that in more detail in a minute, but The idea is that instead of having a lever that holds the chip in place, it's actually soldered into the socket. And this allows it to have functions for smart applications and things like that. So for things that don't use basically a modified Raspberry Pi, these actually have a low-cost computing availability sequence that they can provide that allows functionality for much more complex operations in the receiver or similar items. NLX cards we don't see quite as often. They tend to be really big. They're a little bit bigger than a full-size ATX card sometimes. They're low profile, so they're very short vertically. They're low end, so they're not going to be really high capacity in terms of expansion slots and things like that. It's meant to just provide connections. Again, kind of what you see with the mini ITX, but much more budget focused. It also uses a riser card to attach its components. That's the reason why it's so large. A riser card essentially turns components 90 degrees. So instead of a video card being perpendicular to the motherboard, it puts it in parallel. So it puts it flat to where it's in the same plane. And here we can see a comparison between the big three. You can look at the mini ITX on the right and see that if we were to turn it just a little bit, you would be able to essentially fit two of them on a full-size ATX board. Now that's not to say that in certain circumstances that mini ITX will always be inferior to ATX. It happens a lot, but it's not a for sure thing. It depends on the implementation. But the idea was here, we're able to save costs. When micro ATX was deployed, it meant that people who previously were looking at computers that had, $5,000 to $7,000 price tags were like, hey, we can find something that fits a little bit more comfortably in our price range, still be able to enjoy some at-home computing. Maybe we don't need quite as much customization. We can use it straight out of the box for word processing, basic printing, things like that. That's something that we forget with the perspective of history, is that these motherboard designs were developed 25 years ago. So this is stuff that's been floating around for a while, and the nature of home computing was very different in the mid-90s, and especially in the late 80s, early 90s, when proprietaries were still floating around. Now let's talk about processors, chipsets, and sockets. Now, some people, usually those who are not quite as well versed in the terminology and the items in question, will use these terms interchangeably. I will caution you not to do this. Do not mix up the idea that a processor and a chipset and socket are all the same thing, or they're all interconnected, to where you can just swap out the terminology. That's not how that works. A processor is a physical component. A chipset is a secondary physical component that helps to regulate the operation of that processor, and the socket is a port or interface on your motherboard that the processor connects to. Now, the chipset works with the CPU, as I said, in a regulatory capacity to control memory access, access to the online buses, and certain peripherals. When the system is first designed, we have to make sure that the chipset and the CPU play very nicely together. A socket is just going to have either pins or pads, these little flat contact points, to transition information from the CPU into the motherboard. In order to lift the chip out of or into the socket, they have what are called zero insertion force connectors. Now these are going to apply pressure evenly across a chip in order to help prevent accidental pressure damage. On the right hand side, just as an aside, we have the two major manufacturers in the current market, AMD and Intel. Another big one, which is Texas Instruments, provides the internal chips that you use for things like graphing calculators and other stuff you might see more so in math class than in your PC. Land grid arrays do have a form of pin, but the pins are very, very shallow, usually to the point where they seem flush with the surface of the chip itself, where it lodges into the socket. So this format, as claimed by Intel, who uses it, has a superior level of stability and connectivity. Now we can see from some certain physical properties why this might be the case. The broader pin means that there's going to be more potential physical contact and therefore bandwidth between the CPU and the motherboard. We also have a situation where you're not going to have pins that are protruding from the surface of that chip that could cause, twisting and damage and things like that, and pins that will break, what have you. Pin grid arrays, which is what AMD traditionally uses, have uniform holes around the socket to receive pins from the processor. So when we talk about something being LGA or PGA, we're talking about the chip. We're not talking about the receiver socket. Okay, so the PGA format has these long, thin metal pins that go into the socket and contact a transfer point at the bottom. So exactly the same method of touching, a land to a pad in the socket. You have these longer pins. Now this means that it is going to be very snugly fitted. There's going to be a lot of friction holding it in place, but there is also a lot more potential for damage, to where if a chip gets twisted, or things like that, when during the extraction process, if something gets bent, it can be very, very difficult, if not impossible, to try and replace. Now, PGA sockets can also be set up in what's called flip chip form. Flip chips are, besides being kind of fun to say, are chips that are flipped over. The flip makes sense. So that the usual top of the chip, what we would see as the cover, would be on the bottom, and it contacts the socket. These are not compatible with standard PGAs. So if you have a pin grid system, you can't use a flip chip PGA and just turn it over. It has to be a flip chip style specifically. You also have what are called staggered pin grid arrays, SPGAs. These try to fit more pins in a smaller space by basically setting pins at an offset. So you'll have one row that starts at what we would consider to be a 0 point, and then the next one would start at 2 and 4 and 6. We have this little bitty gap in between them. The next row will have the gap as the start point. Makes it kind of a diagonal grid. Ball grid arrays, as I said earlier when we were talking about the sockets that are used for small form factor boards, these are soldered in place. They're not really sockets in and of themselves. The Atom processor for an ITX board would be a prime example. So if you go and you go to Costco or Walmart or Best Buy and you look to purchase a new receiver for your home, if it says Intel inside or something similar on the sticker, you're probably looking at an Intel Atom. So here we can see some physical representations of that. You can see the BGA has kind of these little, they look like little balls, and it's just the very broad contact points where the item is soldered into the board. And then the SPGA, you can see that we have some rows up top. Let me switch over my laser pointer real quick. So we can see that we've got some pins here starting these very top corners, and then they step in just half a spot and make a row there. It works, but it's not as efficient for more modern CPUs. You get some interference issues on occasion. And then here we see the FCPGA, to where the pins that would connect to the socket normally are on the top instead of the bottom. So let's talk about Intel specifically. Intel has some current chipsets that we're aware of, like Skylake, Kaby Lake, and Coffee Lake. Even far back you can reach to 5th generation Broadwell and Haswell. Now, since the 2nd generation of Intel Core family processors, we can know what generation of process is by its model number. So if we say a Core i5-6200U, we know that it is a 6th generation 200 class processor. So the first number in the 4 digits tells us what generation something belongs to. So if we have an i7, 8850, that's an 8th generation chip. We can pick it out pretty easily. So here we can see an 8th generation LGA 1151 with the cover removed, and load plate is lifted. So the load plate is that big metal frame that kind of sits over the chip. What happens when we lower this into place after the processor has been received is that the lever, the little metal bar that looks kind of like a question mark sitting off to the right, locks in place underneath a little tab. And the way that the bar is bent at the base, where you can see those those little screws that hold the socket together, the pressure of that holds the back of the plate in place and firmly presses it down to hold the CPU against the socket, keeps it from falling off or shifting. So here are some current sockets that we use for LGA desktops: 1150, 1151, 1155. If we're talking about more high performance items or servers, we talk about the 1366, the 2011, and the 2066. So here we have a 6th and 7th generation. There's really not a whole lot of physical difference between them. It's really more so a chipset interaction. And you can see that the bottom of the Intel processor has been kind of positioned against a component there to show you how they line up. So you can see that the pins on the socket, the little blunt pin connects for the LANs on the chip itself, are spaced so that there's really only one way they can go in. Now, something that we need to be paying attention to is that in the bottom corner, left corner of the chip, where it's sitting, you can see that one little gold dot, okay, off by itself. That is not a pin connected off by itself. That is what's called a registration mark. That registration mark helps to indicate what direction the chip should be faced in order to process information correctly. Make sure you're not damaging anything. You'll also see that there are notches on the bottom right side of the chip as well as the top right that will indicate the posts that help to orient the chip in the socket. So here we can see the load lever it's lifted, it's ready to receive a processor. The socket is in an open capacity. Then once the chip is in, we go ahead and shift the load plate and the lever back into position, and they will lock against the retainer screws that hold them in place. AMD, a little bit different again. Remember, we're talking about pins as opposed to LANs this time. AMD currently uses what's called the TR4 socket for its high-end Threadrippers. That uses the AMD X399 chipset. There's also the AM4 system, which is a chipset and family socket set. That's used with the AMD Ryzen and Athlon processors. I currently use a Ryzen 3600, Ryzen 5, with an AM4. AM3 and AM3 Plus are used with pile driver and bulldozer processors, and FM2 is a legacy PGA that's used by A-Series, Athlon, Excavator, and Steamroller. Now, of course, whenever we're installing these things, we should have done a substantial amount of planning before we even sit down with a box. We should be able to identify whether or not a particular socket and motherboard should be compatible. And that is something that we define by checking compatibility on the manufacturer's website more often than not. So we need to make sure that not only does the motherboard support the chipset physically, that they are correctly compatible with the chip in question, but that the logical operation fits as well. So we're not just checking to see if the socket fits, we need to make sure that the chipset and CPU can communicate. To match a processor and socket, of course, we can check the manufacturer's website. We can also check the CPU's manufacturer website, Intel or AMD, and that will help us to identify whether or not a chipset is compatible. Buses and expansion slots. How do we add more functionality? So we have what are called traces on the top and bottom of your motherboard. These are fine lines that represent circuits or paths that enable data, instructions, timing signals, and even power connections to move from component to component on the board. So these are the little wires internal to the motherboard that feed all of those pieces of information I just talked about from one component to another. The bus is I would say, a bus is just a representative name that we use to talk about a pathway for communication. It's just a route that the information can take. Now, in order to make sure that information is correctly interpreted, we have to use what are called protocols. Protocols are just a set of rules for communication set up between two entities. So it could be, two people, it could be a telephone, it could be a computer network. Protocol is just a set of rules and expected behaviors. In order to keep all of these things synchronized, we have to use a special internal metronome called the system clock. This is usually a quartz oscillator or similar. So whenever we have data passing through components, it's sent as oscillations of voltage. If we have voltage present, we say that it's true. If we have voltage missing, we say that it's false. The data path size of a component is the width of a bus described by measuring the trace count. Now, traces, because of how binary mathematics works, are measured by powers of 2. So 2, 4, 8, 16, etc. We can see on the graphic on the right that we have a memory chip and a CPU, and there are 8 traces between them, so the DPS would be 8. It is passing in what's called parallel, one instruction 8 bits wide. So we can see 0, 1, 0, 0, 0, 0, 0, 1. That is the representation of the letter A, capitalized, on the 8-line data bus between the CPU and the memory. Now, serial versus parallel transmission is something that's been, contested, especially with more modern distribution methods for signals as being sent from multiple devices. But the traditional thinking is, when we send things in parallel, we're sending one instruction at a time in a complete form. And that's all well and good. But because of the speed at which we like to transmit things, if there's any disruption to the signal, there may be information that gets lost or scrambled as it's passed from one component to another. What is considered to be more effective in that case is to use serial transmission, where we send one bit at a time per data line, so that no matter how fast or slow it always arrives in the correct order. So if we send 8 different instructions in serial, that should be just as fast, if not faster, than sending 8 instructions in parallel. Still 64 bits being moved, 8 by 8, but making sure that we don't have to keep resending because of scrambling or lost packets or anything that gets damaged in transit tends to be much more effective over time. So here we can see on the bottom of the motherboard, underneath some of the lacquer, how the traces for the various components all line up and migrate towards the central processor socket. Everything kind of converges on that point, especially if you're looking at your expansion card slots or things like that, those big rows of little silver connection points. You can see that those are all kind of coming in towards the processor socket. The most common expansion bus that we use in modern computing is the PCI Express interface. PCI Express is available in 4 different sizes, and we have what's called X1, X4, X8, and X16. I don't think they ever did an X2. I don't think they felt like it was necessary to make a completely different slot for that. But other than that, you can see that it follows the powers of 2 we were just talking about for DPS very well. The number after the X is what refers to the number of lanes available for data transmission. So when we talk about lanes, we're essentially talking about like lanes on a highway. So if we have a 4-lane highway, that means we have 2 going, let's say it's, I-40, 2 going east, 2 going west, or I-95, 2 going north, 2 going south. Those lanes are basically always there as conduits for traffic to move up and down. It's not going to switch them around to try and accelerate things. It's just dedicated transition paths. An X16 slot is traditionally used by something that requires a lot of throughput, such as a graphics card. So in order to provide that throughput, we have to have more wattage. We have to have more power consumption going through that card at a single cycle. So we'll have to use extra connectors, sometimes 1, 2, or even 3. The new RTX 3000 series cards from NVIDIA are actually going to use a new 12-pin connector, which is a modified pair of 6-pin connectors in essence. There are going to be some adapters out for a while, but more modern motherboards will probably come with a 12-pin option, if not through a modular system. So here we can see 3 types of expansion slots together. We can see that there are 2 conventional PCI slots, 2 PCI Express X1s, the really short ones, and then you can see the X16s rendered in red. And you see that they have those little lock tabs at the back. This is a Fatality branded ASRock motherboard, built for gaming most likely. But you can see that the traditional PCI slots there mean that this is probably a slightly older board in order to support legacy components. Original PCI is nowhere near as fast or as stable as PCI Express, so it's only included on motherboards that need it for legacy accessibility. So I would say this board was probably built around 2004 or 5. So PCI Express is not considered backwards compatible. It does not work with PCI or PCI X. It does use serial transmission, which is all to the good. That's what we want to see, as opposed to standard PCI's parallel transmission. Now, on the right-hand side of your screen, you'll see that there is a graphic from Hardware Secrets, which is a great site. I included a link there in the bottom if you pull it from the actual lecture slide. But if you just go to hardwaresecrets.com, you'll see some really good graphical representations of why certain aspects of your computer behave the way they do, or why they were designed the way they do. I know a lot of people are graphically oriented, so I do definitely recommend that site if you haven't seen it. We do have a couple more images from them in the slides as we proceed today. And that is supposed to say ordered, not ordined bits at the transmitter. So you can see when things are being transmitted, what's called the TX end, they're in sync. They're lined up correctly so that a 1 looks very clearly like a 1, and we're not losing any what's called phase. When we get to the opposite side, the what's called the RX side, receiver, you can see that the bits are now shifting slightly and they're not lined up. So when we start dealing with stuff that's transmitting in gigabit or even terabit eventually, we would need to make sure that all of those transmissions are lined up correctly, and that's why parallel tends to be a choice that we do not follow in the same capacity anymore. Serial tends to be the way to go. So here we can see some visual representations of what the different PCI Express slots look like. You can see the X1, shortest of the lot. The X4, about double the size. The X8 probably another 50% over, and then the X16 probably another 30 or 40% above that. So the X16, you can see, is probably about 5 or 6 times larger than the X1. So this is not a what's called a linear scale. This has got a little bit of a logarithm to it, so that way it's not fully, an X16 is not double the length of an X8, not double the length of an X4, or 4 times the length of an X1. What does change in terms of performance is the number of lanes available for transition, as well as the amount of power that can be delivered from the motherboard. So in PCI Express version 1.0, we had a 150 watt power output. 75 watts came from the pins that directly allowed connection to the board itself, and then there was an additional 6-pin connector that provided another 75 watts. Then we moved up to version 1.1, added a second 75 watt 6-pin connector. Version 2.0 pushed us to an 8-pin connector using 150 watts. Now we have 32 lanes instead of 16. And we have a second connector using either Molex, 6-pin PCI Express, the standard auxiliary we've seen for the previous 2 versions, or SATA. So you can use the same SATA power connector you would for a hard drive for this new PCI Express power enhancement. So PCI Express versions 3 and 4 are now focused not necessarily on increasing the number of pins or power or what have you, but by adding speed. We're trying to make the best of our lanes of transition here. So the grouping of lanes to where we have an up lane and a down lane for a connector allows us to multiply the bandwidth that's possible for each connection. So if we have a PCI Express X8, we're going to identify that we have 8 lanes transitioning information at 500 megabytes per second. Now notice that I use the term bytes, not bits. Whenever you see a lowercase b, that's bits, uppercase b, that's bytes. So 8 times 500 is the same thing as saying 4 times 1,000, or 4 gigabytes. 8 gigabytes is what the output would be for a 16x slot, because as you can see, we're using 16 lanes as opposed to 8. Now, why don't we have 32 lane connections? Well, if you look at the graphic on the right, again, you see that for the lane to work properly, it has to have an up line and a down line. So that means that we take 32 lanes, which is what we brought in with version 2, and we split it into groups of 2 for each lane. We have up and down. So 16 times 2 is 32. So we're basically cutting the board in half in terms of its functionality to ensure that we have full duplex transmission. So here we can see a couple of different comparisons between PCI versus PCI Express, etc. And I'll even throw in, because it was in the graphic to begin with, a little bit of AGP. So let me grab my laser pointer again, and we'll look on the left here first. We've got our PCI slots. These are standard PCI. We've got PCI X1, little slot over here, and then we've got our PCI Express X16 on the far right. And you can see that PCI Express X16 and X1, even though they are generally similar, you can see that they have kind of that double pin connection, they have a little registration notch. They face the opposite direction. That's a big one, to make sure you don't accidentally try and fit an X16 card in a PCI slot or vice versa. And then the PCI slots themselves, if you look at the motherboard traditionally, are a little bit taller and a little bit thicker in width. Now let's take a look over here at the different cards that will actually interface with these devices. And something I'm very happy with is that the people over at Hardware Secrets decided to use two cards that were very, very similar. We have the GeForce here that is PCIe connecting, and then we have one that's AGP connecting. Now AGP stands for Accelerated Graphics Port. That's a little bit of an older connector. That was more so around the time when I first really started getting into working with IT tech in a more professional capacity. It was right out of high school. You can see that the pin breakup is a little bit different. You can also see that it's a little bit more rounded around the edges. Now they did introduce the little retainer clips, the little security connectors that you see in PCI Express, but the pins are a little bit thicker and rounded the way that you see in traditional PCI. Whereas when you get to PCI Express, you see that the edges are much sharper and the pins are much thinner, meaning that they're trying to fit more pins in the same space. Now, this is just a little bit of documentation for a motherboard to explain how PCI Express works in relation to the slots. So this has one PCI Express 3.0 X16, one PCI Express 2.0 X16, two 2.0 X1s, two standard PCI, and it supports Crossfire and Crossfire Quad. So Crossfire was just basically the ability to try and connect two slots together by using a bridge to increase their functionality. So note here that there's a little asterisk down at the bottom. It says if PCIe 1 or E3 is occupied, PCIe 4 will run at X2 mode. So that means that if you have PCI 4 at X4 mode, then the other two cannot be occupied. PCIe 2, which is our standard X16, runs in an X16 mode regardless. But the 1 and 3, which are our 2.0 X1 slots, are basically borrowing lanes from the other two. So essentially, if 1 or 3 is occupied, it cuts 2 lanes out of the X4 or the E4 slot. Here we have some of the auxiliary power connectors we were talking about. We can see that the SATA is on the right, Molex is on the left. Molex is very similar to a lot of USB connections because it has 4 primary leads, one hot lead, one ground lead, one neutral, and then it has a 4th for data transmission. So you have some different swap arounds that can be done with that. So original PCI, I'm not going to go too deeply into. It is part of the process of learning about PCI Express. The idea was that PCI transmitted things in parallel versus PCI Express that goes in serial transmission. It's no longer considered to be evolving. You know, it's something that's considered kind of a dead standard. There are legacy items that use it, which is why I assume they include it on the test. There are 4 different types of slot based on whether or not they accept 32 or 64-bit transmission, and based on whether or not they operated at 3.3 or 5 volts of voltage, you know, power transmission. So we see here that if we have 2 different cards, 32 and 64-bit, and we have 2 different power supplies, 3.3 and 5, that means we should have at least 4. But then if we look at the universals that are just below the 5-volt cards, you'll see that there's 2 that do both. So that's how we get 6. It seems a little weird until you look at the graph. Here we can see what's called a riser card. We talked about this a little bit ago. It makes a connection parallel as opposed to perpendicular, so it does a right angle connection to turn a device. You can use this for all kinds of stuff. You can use it for PCI, PCI Express. You can use it for RAM in certain cases. If you ever look at a laptop, traditionally the RAM is going to be connected to a soldered-in riser card system in order to make it parallel with the board to reduce the amount of depth needed to store it. Now, onboard ports and connectors are directly integrated into the motherboard and are considered to be not necessarily superior, but the preferred mode of connection when you're first setting up a new machine. Then after you've installed your drivers and things like that, you can start adding peripheral cards to replace it. So if you ever run into an issue with a brand new motherboard, bear in mind that it's supposed to kind of be set up naked before you start adding in, graphics cards and audio cards and things like that. You may see things like USB, very common, PS2 ports, which are old school mouse and keyboards connectors, video card slots, sound slots, etc. The I/O shield, which you see on the right, is a metal plate that covers the space between the port holes for different I/O objects on the computer. There are also internal connectors we may deal with, such as an internal USB hub, M2, part of the NVMe system, SATA, and IDE. IDE is also known as PATA or Parallel ATA, and that is a predecessor to SATA. So here we can see the I/O shield removed and just the various I/O devices exposed for a Vengeance style motherboard. This is a Corsair Special of some kind. You can see that there are sound ports. There's 3 instead of 6. This is probably a micro ATX. I don't think it's a full ITX at this point, but you can see that there's 2 different graphics ports. One is DVI, one is HDMI, which, for those in the know, HDMI is a form of DVI. And then of course you can see that you've got USB 2.0 and 3.0. 3.0 shows up as blue. And then the I/O shield fits the ports to the case, make sure that there's minimal loss of airflow. SATA stands for Serial Advanced Technology Attachment. Parallel Advanced Technology Attachment is the parallel equivalent, and this is used by most conventional storage devices today. I can't think of anything that I work with on most of my machines that don't use SATA, unless it's something like NVMe or M2. So M2 was previously known as what's called the NGFF, Next Generation Form Factor, and it's used to connect mini add-on cards. You can add solid-state drives, kind of like, they almost look like little RAM sticks, or you can add a wireless card. So a lot of the new 5G cards for laptops that I've seen designed, those are going to use the M2 slots in order to speed up connectivity. Here we can see an M2 slot in a standard desktop motherboard, and we can see that there are 3 different screw holes to anchor this particular device. And you can see that each of those positions is spaced a little bit differently, and that's because each of those cards, being a different size, has to anchor their end to make sure that it doesn't wiggle its way out of the slot. You may also see different slots based on what are called the keys. M2 slots are keyed with a notch to hold cards with either a B, M style, or B and M style edge connector. So that essentially means that there will be pins that are left off in order to allow connectivity. So here you can see that the B key connector on the left has pins running from 1 to 11. So you've got your 6-pin width there. You've got a space going up to pin 21, and then from 21 to 75. On the M key, the pins are on the opposite side, so you've got 5 pins wide coming from the end and cutting in, going from 57 to 67 for the blank. If we combine those 2, then we get the B and M style. IDE, or Integrated Drive Electronics, was a 40-pin ribbon cable style that was used to connect hard drives prior to SATA. The thing about IDE was that usually you only had 2 connectors on your motherboard, and each of those connectors could support 2 drives, usually. That's where you had either cable select or jumper based selections to set which one was considered to be the master drive and which one was considered to be the slave drive, where the master drive would traditionally be where your operating system was stored. USB headers, if you guys think back to our first teardown lab, you'll remember that there's that block of 2 rows of 5 pins, one of which is dummied out in order to provide a USB connection. So here's our IDE interface, and you can see the cable just above it. And here are the USB 2.0 connectors. If your motherboard didn't have the cabling or the header damaged for it. You may have also seen that really thick blue rectangular connector for the USB 3.0 connectors for the front. So that's where those come from. They just tend to have a couple of extra leads. Now, speaking of the motherboard interfaces, let's talk about how they're configured. How do we turn certain things on or off? How do we update? And that's using firmware such as BIOS and UEFI. Firmware on the motherboard is used to enable or disable a component, so connector, port, whatever, to control the frequency and other features of the CPU. This is how we do overclocking or underclocking if necessary. Manage security features, control the order of operations when the system first boots, as well as monitoring and logging various activities of the board itself. Now, logging this information through the motherboard rather than doing it through the operating system gives us a different level of control. When you're trying to do something through the operating system, there's layers of interpretation that have to be processed, which means certain types of data can be filtered out. That's not necessarily what we want. We want a log system that we can review that is absolutely accurate to the physical operation of the device. Motherboards made after 2012 almost universally use a BIOS/UEFI combination firmware. Prior to 2012, standard BIOS was what was used. UEFI, the Unified Extensible Firmware Interface, improves upon BIOS, but also includes it for what's called legacy compatibility. So you'll often see what's called the CSM, or Compatibility Support Module, listed in the BIOS of your motherboard when a BIOS compatibility module is present. Now, UEFI is required by Microsoft to boot any system that is considered to be certified for Windows 8 or 10. So from Windows 8 forward, UEFI is a requirement in order to have a Windows boot partition. It's also something that's necessary for any hard drive larger than 2 terabytes in size, so 2048 gigabytes. UEFI also offers Secure Boot, which prevents a system from booting up with drivers or an OS that is not digitally signed and trusted by the motherboard or computer manufacturer. So if you don't have the correct platform keys or signatures, certain operations can't even be carried out, such as just booting up a hard drive. Now, from backwards compatibility standpoints, we can boot from what's called an MBR drive and provide BIOS boot through the CSM. So that's why the CSM is traditionally present, to allow non-compatible drives to have a workaround. It just means that we have to go in and turn that on so that we can be sure that we're actually authenticating that process and not circumventing Secure Boot on accident. So to access Secure Boot or any other aspect of BIOS/UEFI, we have to use the correct key press during the boot process. Now, most of the time, because of how fast the timeout process is, I generally recommend just spamming the key in question as soon as the power kicks on. More often than not, it's F2 or delete. Sometimes it'll be F12. F11 is traditionally the boot menu. Sometimes you'll see stuff on F6 as well. Once you've gotten to the setup screen, whatever it is, you will see the menus and help features kind of start to come through, depending on whether or not it boots to a command line style or a GUI style. Now, UEFI is by default set for a GUI interface, meaning that the mouse works as opposed to just the keyboard, and you also have much more graphically robust menus. So here we can see a command line style system. They are using color, they are using graphics, but that is still part of the command line system. Everything that you do has to use the keyboard as opposed to the mouse. You can see in the bottom right corner the legend of how we're supposed to navigate these different menus. Here we can see in UEFI that it looks a lot more like a standard computer program we'd be used to seeing in Windows. You can even see the mouse cursor in the middle hovering over the button that says ASUS Optimal. And you can point and click rather than having to do things with your keyboard, though the keyboard will still work. In the boot menu, we can set the order in which the system tries to get started from certain devices. This is also called the boot priority order or boot sequence. The boot order may need to be changed if we want to use something like booting from an external flash drive in order to perform an upgrade, or if we want to, copy things over between two computers and we don't want to use the Windows system. We want to be able to use something like, RoboCopy built into Linux or something similar. If we're installing from a server, we'll want to switch over to what's called the EFI network option in the LAN connector to make sure that it looks for an installation request submission at the top of the boot. So that's what's called a PXE boot, or PXE. We can also boot from a DVD. If we have a bootable DVD, we can use that to either install an OS or fix an operating system that's not working. Secure Boot is a really useful tool that was invented to help prevent malware from launching before the operating system, because the operating system obviously is the overarching structure of the interface that we're used to using, and that has to launch antivirus. If something can load before the operating system does, or before the antivirus can, then it's not going to get detected in the same way. It may be able to carry out certain processes. So Secure Boot only works when the mode is set in UEFI and the operating system supports it. If we're running something in CSM, like if we're using an old MBR hard drive, Secure Boot will not work. So just bear in mind that you can't install Windows 8 or Windows 10 on an MBR drive that's running through CSM. It becomes alphabet soup after a while, doesn't it? Now, Secure Boot is supported by several Linux distros as well as Windows 10 and 8. There are digital signatures, encryption keys, and specific what are called vested drivers that are stored in the flash memory of the motherboard in order to verify that they are a trusted resource. It'll go ahead and check all of these against the Secure Boot databases and make sure that anything that is trying to boot is not dramatically different from those previous lists. So here we can see that the factory keys are being restored for this particular AMD system. You've got some platform security here turned on or off based on what you need. And it will help to read your documentation and be aware of what you're saying yes or no to when you modify these options. Now, the boot screen also allows us to select whether or not CSM is considered enabled. If we're going to use Secure Boot, we have to make sure UEFI mode is turned on. So here we can see the options for setting up the boot configuration, whether or not we have any interrupts, what ROM messages may or may not show up, how long the post takes to complete. Basically, we can delay it a little bit longer if we want to have time for options. Usually, as I said, you have to kind of spam the button just to be able to get the menu up because it goes by so quickly. So one of the options that I want you to see up at the top is Fast Boot. It's the one that's currently highlighted in light blue, and it says that it is disabled. That is the option that I traditionally use. Fast Boot essentially stops some of the security checks that we talk about when we're looking at platform security, and that is never to be encouraged. So I will always recommend that Fast Boot be turned off, especially in the modern environment where we use solid state drives to where the boot process takes less than 30 seconds anyway, even on a bad day. Now, in UEFI, we can actually go in and turn certain things on or off. So let's say we install a new graphics card and we no longer want to use the onboard video. We can go in, turn it off, and boom, we can focus on using that graphics card. Now we want to make sure the graphics card is correctly installed and functioning, because if we do that, it will go from the UEFI system to a blank screen and nothing will come up because that port has been turned off. Now, what you can configure depends on what your motherboard is, who the manufacturer is, and what firmware updates are present. You can also go in and modify certain devices such as your processor, your memory, even your video card to run at a higher speed than the manufacturer recommendation. Now, if you do it correctly and you have sufficient cooling, you can eke out some extra performance. But it's not a recommended best practice. So I tend to leave overclocking alone. That's just me, mostly because the equipment that I buy is perfectly suitable to my needs. But I know for some people it's very much a endless pursuit of I got to get a 144 frames per second and this resolution, what have you. So here we can see just a listing of some devices being manipulated in UEFI. Now, some other features besides Secure Boot. Power on passwords, being able to deal with a password having to be entered when you first boot the machine. LoJack, which can trace a stolen device. Drive password protection, to where a hard drive won't even boot unless you've entered a particular password. TPM chip, this kind of ties in with the encryption item, except it uses what's called a bootlocker platform key, where essentially there's a key generated by your motherboard when you first do the encryption, and if your hard drive is ever removed from that computer, it will no longer recognize the same platform code. So that means that it will say, nope, not the right one, I'm not going to activate. You can't access anything on the drive because it's fully encrypted. And then drive encryption as a standalone is also available. So, you can set login passwords, supervisor passwords, all number of things. Again, check your documentation. Here we can see the different password access levels for various users. And we can see here an explanation for how LoJack works. It does have to be connected to the internet, but with the profusion of Wi-Fi, if somebody stole your laptop and you activated LoJack, there would be very few instances in which I could see someone trying to conceal what they're accessing, or being able to in any event. And it does also require a subscription. If you sign up for LoJack for a year and then somebody steals it in month 13, you're no longer covered, so they're not going to be able to just automatically turn it back on. The TPM chip and hard drive encryption process means that the drive cannot be used on multiple computers without backing up the code. The key can be backed up to a flash drive or something similar so that you can then access it on another device. Another thing that we need to look at here, and we'll see again in later chapters, is what's called virtualization. Virtualization is where we essentially partition off resources of a physical machine in order to create a secondary non-physical machine, hence the term virtual. The virtual computer has a motherboard in virtual space, has a processor, has RAM. What it's doing though is just kind of slivering off pieces from the original and co-opting it for itself. Now this is perfectly acceptable. It's really good for security testing because essentially it's like you have a computer that cannot necessarily be manipulated externally. It is entirely run in software, so that means that the responses are facilitated through what's called your hypervisor, or your host operating system. Now, once we've gone in and we've made changes to UEFI or BIOS, we need to make sure we save those changes if they're considered to be desirable. So we need to make sure that we press something like F10, or the exit screen will usually have like save and exit or discard, and make sure that you only save changes that you're sure are working correctly. You should still document as you're going through what we call the change management process, so that if there is an issue, people know what kind of work was being performed. Now, you can sometimes have an issue where you've made a change which doesn't immediately make sense as being conflicting, and the system is still operating poorly. If you need to flash back to an earlier configuration, usually you can just hit the button that says load optimized defaults or load defaults, and that will allow you to go back to the factory settings for that particular device, and then you can work your way back up with various edits. Excuse me. Here we see the ASUS BIOS utility exit screen, and you can see there are three primary options: load optimized defaults, which we just talked about, save changes and reset, and then discard changes and exit. So it's saying, we can either go back to scratch from the defaults, we can save the changes you just made and add them into what's already there, or we can discharge what changes you've already made and only keep what was approved the last time we had a yes on the save mode. Now, we've talked about firmware, we've talked about how the control software for the firmware works. We also have to look at how that firmware communicates with hardware directly outside of the motherboard. And that happens between the OS, the motherboard, and the hardware through what's called a software driver. When a motherboard's causing problems, we may need to check to see whether or not the drivers are out of date, or if the UEFI hardware or software interface is no longer in date as well. So software drivers are just little pieces of code that essentially allow facilitated communication between two non-similar entries. Imagine that you worked at the UN as an interpreter and you had to deal with translations between somebody from Bulgaria and somebody from Namibia, for instance. You know, very different areas of the planet, very different alphabets in certain cases. So whenever you first set up a machine, traditionally there are what are called generic drivers that may automatically be installed. There are also other drivers that may be installed through what's called plug and play, which is where a new device is associated with the system. They will go ahead and update it to the most current version it can access, so that your whatever you've got is at its best possible version. Now, after we've installed a motherboard physically, there's usually a CD or DVD that's included that allows us to go ahead and make sure that if there's any drivers that don't seem to be working, we have a clean manufacturer approved source, and then we can run something like, I'm trying to remember what the one is for Linux. I think it's apt-get, but you can do a driver update that way. And then for Windows, you've got Windows Update, and they'll automatically process that. Just make sure that you are getting the correct drivers for your board as well as for your operating system, because it's interpreting between those two things. If your operating system is a 64-bit version, you have to make sure you have 64-bit drivers. If you have a 32-bit driver, you better make sure you have a 32-bit OS. So here we have a kind of a screen grab of the ASUS website where we could pull info for the Prime Z370P. And the funny thing is that it's a very simple click and drag for you can get one driver, or you can get like a desktop-based client that will automatically download everything for you. Just depends on what you feel you need. I tend to like checking it in this order. I get my manual so I can keep it on hand. I get my firmware so that way I know the motherboard is operating at its best possible configuration, and then I go driver hunting. And traditionally I only go driver hunting if something isn't working, simply because Microsoft Update traditionally pulls the best version available from the web. Now, if we need to upgrade the firmware of our device, which we just talked about, we need to know that the process is called flashing and can be very dangerous if you've never run it before. Now, very dangerous, I say, simply because people who aren't used to working with it don't realize how sensitive that process is. You're essentially updating the underlying instructions for a motherboard, and if that goes wrong, how are you going to reset it? So unless the manufacturer has included something like flashback or some other particular process that will allow you to go back to an earlier version of firmware, it can be very daunting to not perform what's called a brick. You don't want to brick your device. Essentially, it makes it into a useless piece of material, like a brick. Now, bricks aren't intrinsically useless, but they're not great for running computers, now are they? Now, we only want to do a flash when we have a problem, more often than not. Let's say that, if everything's running smoothly, we just want to leave that alone. If there's a certain feature that is now available in the flashing firmware, then yeah, you can definitely talk about running a flash, but I generally only do it when something's going wrong, because there is so much potential for something to go sideways when you're doing it. So in order to perform the flash, let's go ahead and read our documentation. Can it be done internally? Can it be done from within BIOS or UEFI itself? Can it be done from within your operating system? Can it be done using a flash drive? There's a number of different options that are possibly there. Some things to be aware of when you're updating your firmware is make sure that you have a backup, and make sure that once you start the update that you don't mess with it. Now, in order to clear your BIOS or UEFI settings, not the firmware, but just the settings, there's usually what's called a reset jumper. Jumpers are just metal pins or posts that stick up off the motherboard perpendicular to it and can be used like a light switch. So an open jumper, for instance, has no cover, and you see that the pins are just kind of sticking there blank. A closed jumper has a cover on the two pins that is lined with metal, which means that it is conducting electricity between those two pins. Now, in order to clear your password, you'll have to make sure you know what configuration is which. So here we see the jumpers on a motherboard. We can see this instance where they have no jumpers set active in A, so there's no pins being covered. In cover B, you see that there's one being parked. So you see that there's one pin covered and no other pins are covered. So 5 out of the 6 are completely open. That's just a place to store it temporarily, but if you were to move it over, and connect, say, pins 1 and 4, a result would most likely occur. In step C, it looks like they're doing something very close to that, and that's where we have one jumper active to change a particular setting. So here we can see a configuration jumper, just kind of an example. So we've got pins 1, 2, and 3, 1 being the top square, then we've got 2 here, and then we've got 3 at the bottom. 1 and 2 is normal, 2 and 3 is configure, no pin covers, completely blank jumpers is recovery mode. So this allows us to do some different options. Now this isn't going to work for every device, but it'll work pretty often, because again, with non-proprietary implementation, why wouldn't we all use the same shortcuts and commands? Now once we've gone in and made some changes, we want to make sure those changes are preserved, and that is done by using what's called a complementary metal oxide semiconductor. It's a little piece of RAM that's attached to a watch battery, little CR2032, that retains this data magnetically even in the absence of AC power. So if we have a supervisor password, or if we have a drive or port that has been disabled, or if we want to create a RAID array, things like that, all of those manipulations need to be formed in the CMOS so that it can be safe in the event that your computer loses power. Otherwise, every time you shut down, turn the computer back on, you'd have to go back through a lot of the configuration process over and over and over again. Now, if we're going to replace the CMOS battery, let's go ahead and select the replacement. Again, most of them are CR2032s. Your mileage may vary slightly. Then we're going to go ahead and power down the system, unplug, discharge. We're going to hold that 3 to 5 second power button, and then take off our case cover. While we're using the ESD strap, we're going to go ahead and pop the old battery out with a flathead screwdriver and put a new battery in place. Once that's done, we can just go ahead and plug everything back in, close it up, and everything should be fine. Gratefully, CMOS batteries are not difficult to replace, so it's important that you just make sure that you're following the steps provided here to not accidentally shock another component. Now, if we have to install or replace a motherboard, that can be a little bit more tricky than just configuring one, as you might imagine. Motherboards are considered field replaceable units, meaning that they can be replaced with basic tools out at the work site. They don't have to be brought back to the office or taken to a specialized location. They can be, just literally taken out with screwdrivers and fingers. Now, a technician needs to know how to select an appropriate motherboard or install or replace one in a desktop or laptop computer that needs it. So if we need to replace, obviously we're fixing something that has gone wrong. If we're installing a new one, that can be either we've already taken out the failed one, or we're setting up a whole new machine. Now, there are 3 approaches to selecting your motherboard. You can either pick the board that provides the most room for expansion. That would be considered the gold standard, gold because it's most expensive. The board that suits the needs of your computer current configuration and no more, be kind of a bronze. And then the silver option, which is the one that most people use, is to select a motherboard that meets your present needs with moderate room for expansion. So we need to ask some questions to ourselves and to our clients when we're doing this transition. How is the motherboard going to be used? To what purpose is it going to be put? What form factor does the motherboard have? What brand of processor does it use? What's the model number that's supported? We need to check the website and make sure we know that. And what chipset does it use? So if we can support the manufacturer, the processor, and the chipset, we should be good. And last, what type of memory and what speed of memory does it use? So how much does that cost? Now, for a desktop, it's a little bit different when we're dealing with a laptop. Laptops obviously are, kind of custom built, but with a desktop, there's so many other choices. What are the embedded expansion slots? What do I have to be able to build this thing out? And then what type of onboard connectors do I have? Does the board fit the case that we plan to use? Do we know what the price is? Do we have a decent warranty? Does the board get good reviews? User reviews are very, very helpful. And you'll have to learn how to read user reviews too, because there are some that are a little bit bot-ish, a little bit AI involved. How extensive is the documentation? How user-friendly is it? And how helpful is the manufacturer's website? You know, do you get an email turnaround in a day or two, or is it like a week or two? Because that is going to be a huge difference when you're in a business situation. What warranty and how much support does the manufacturer supply for the board? So not only do we need to know how long the warranty would last, but what it would and would not cover. And that tends to be a little bit more difficult for people to be aware of. So there's a long list of steps, and obviously I know you guys can read, but I'll give you the highlights. Again, we're going to verify our motherboard, familiarize ourselves early, go ahead and take out the old motherboard if there is one. We'll go ahead and take out all of our various parts. We know the order of operation from going through the lab 1. Go ahead and make sure that all of your installation process is done according to those steps, and then make sure that all of your power connectors are correctly taken care of. Now, something we didn't get to do in class, but something I would like you to do in a professional case, is to make sure that you have good cable management. Have everything zip tied together loosely. You don't have to cramp it down super tight. You just kind of anchor everything out of the way so that you get good airflow inside the machine. Once we go ahead and get everything plugged in, let's go ahead and run the boot process for the first time. If everything works well and goes into BIOS setup, we can then go ahead and do our next phase, which is configuring the BIOS/UEFI. Once we do that, we go ahead and boot to whatever source we need for our operating system. If you have your OS already installed on a drive and you don't need to do it again, that's fine. But if you do need to, make sure that you're, again, following instructions. Make sure you have the correct version that you wish to use. Maybe it's an updated version, that would be good. Make sure that you have a hard drive with the correct capacity and interface. Make sure your data and power cables are hooked up correctly. And then go through the installation process as we will in lab. Once Windows is installed, let's go ahead and verify that it starts up with no problems. Let's make sure that our motherboard drivers are accurate, all expansion cards we put in, and things like that. Make sure your antivirus is installed, make sure that everything stays updated. Now, a laptop is a little bit different. I'm going to read through this a little bit quicker, simply because there's a lot of details in here that don't necessarily apply to what we're going to do. But if you have questions about laptops specifically, let me know. I may have Mr. Vandergriff or Mr. Parker help me film a disassembly process for a laptop, just to show you how much more finicky the screws are, how much more the disassembly process is like taking apart a jigsaw puzzle, and how hard it is to find non-proprietary parts to support a potential failure. One of the easiest things to be aware of is just, again, knowing your order of operations. So we want to make sure we take out the power source first, and then we want to go ahead and look at our documentation and see how everything comes apart. Remember that a service manual is going to be much more extensive than a user manual, so if you can get a hold of one of those for your device, that will help you greatly. Generally, as you're walking through, you're going to take stuff out in a pretty predetermined order. You'll go ahead and take out all the screws for the case. You'll go ahead and make sure that all of the case pieces are organized, labeled. Definitely make sure you keep those together. Photo documentation is helpful here. You'll lift away, ribbon cable connectors, and taking out the RAM is more so kind of like bending a paper clip than the same way it would be on a desktop. You can see here that the motherboard, just like it would be on a desktop, is attached via screws to these mounting points to keep everything balanced. That is our Chapter 2 lecture. If anybody has any questions or concerns, of course, you can always contact me at my Google number, 910-239-7814. You can also contact me at jearmke063 at cfcc.edu. jearmke063 at cfcc.edu. You can also contact me through the messaging through the Blackboard site, or of course you can come by my office, NB226. Anything else? I look forward to hearing from you, but hopefully you'll have a great rest of your day, and I'll catch you next time.